I want you to imagine the apocalypse. And I don't mean the Hollywood blockbuster version.
Right, forget the sudden blinding flash from a massive meteor streaking across the sky.
Exactly. No instant merciful obliteration here. I want you to picture an end of the world that is just agonizingly, painfully slow. A suffocating, boiling, basically toxic end to almost all life on Earth.
Playing out century after century, millennia after millennia.
Yeah. A planetary machine slowly tearing itself apart until the oceans literally rot and the forests just burn to ash.
It's a profoundly terrifying image to conjure up. But the crazy part is, it isn't science fiction. It is the absolute reality of what our planet actually went through.
Welcome to our deep dive into the Permian-Triassic extinction event. Now, if you have any familiarity with paleontology, you probably know it by its colloquial and frankly completely earned nickname.
The Great Dying.
The Great Dying. This happened approximately 251.9 million years ago, and the goal of our deep dive today is to really unpack the towering stack of sources on this ancient planetary-scale murder mystery.
We're going to examine the victims, we'll look at the bizarre and resilient survivors, and we are going to dissect the incredibly complex geological chain reaction that pulled the trigger.
And I want to emphasize why you should care about an event that occurred, a quarter of a billion years ago.
Yeah.
It is profoundly personal.
Yeah, it really is. Because you, me, the dog sleeping on your rug, every single living animal you see outside your window today, we are all the distant descendants of the bruised, battered survivors of this exact catastrophe.
Our very biology, like the way our mammalian bodies function right now, is essentially a scar left over from this specific evolutionary bottleneck.
So to really wrap our minds around this, I mean, we have to start with the sheer mind-boggling scale of the destruction.
Right. When people hear mass extinction, the mind immediately jumps to the dinosaurs, right? The Cretaceous-Paleogene event from 66 million years ago.
Yep, so it's terrible, obviously.
Right, terrible. But the raw data from the fossil record on the Permian-Triassic event paints a picture that makes the dinosaur extinction look almost, gentle.
It really does. We are looking at the total eradication of 81% of all marine species.
Wow.
And on land, 70% of terrestrial vertebrate species were wiped out. We lost 57% of all biological families and 62% of all genera.
It stands completely alone as the greatest of the big five mass extinctions. And there's one really striking detail from the sources. It is the only known mass extinction of insects.
Right. Throughout all of Earth's history, insects have been incredibly resilient. They survive almost everything.
But not this. During the Great Dying, 8 or 9 entire insect orders simply vanished from the fossil record.
And unlike the dinosaur extinction, which was, precipitated by a sudden asteroid impact, so one singular terrible day for planet Earth, this Permian extinction was a prolonged agony.
The data shows it occurred in 1 to 3 distinct pulses or phases. The biological slate was wiped so clean that it permanently severed the continuous timeline of life.
Marking the boundary between two major geologic eras, the Paleozoic and the Mesozoic.
I really want to dwell on that distinction between species, genera, and families because it's crucial. Losing a species is tragic. It's like losing a specific branch on a tree.
Right.
But to put the loss of entire biological families into perspective, think of it like a game of evolutionary Jenga. Instead of carefully pulling out a few wooden blocks until the tower gets wobbly and falls.
The Permian-Triassic event is like someone walking into the room, kicking the table over, and setting the scattered blocks on fire.
Yes, exactly. Let's look at the victims to really ground this. Trilobites, for example.
Oh, the ultimate survivors.
Exactly. These were incredibly successful armored marine arthropods. They had been crawling across the ocean floor since the Cambrian explosion.
And had already survived multiple mass extinctions over hundreds of millions of years.
And at the end of the Permian.
Right.
100% extinct. Every single trilobite lineage gone. Blastoids, which were these beautiful stalked seabud echinoderms, 100% extinct.
And on land, the massive globe-spanning forests literally vanished, leaving the continents basically barren.
The devastation was so thorough that the fossil record shows an almost complete restructuring of the biosphere.
The entire architecture of how life interacted, who ate whom, where organisms lived, it was all dismantled. Life was forced to rebuild from absolute scratch.
Which introduces this massive biological riddle. If 81% of marine species died, what specific golden combination of traits made the remaining 19% special enough to survive?
That is the exact riddle scientists have spent decades trying to solve. And the answer isn't a single trait. It's more about an ability to withstand a gauntlet of different overlapping environmental horrors.
And to understand that gauntlet, we have to establish the timeline, because the speed at which this happened dictates how life could or couldn't adapt.
Right. So the consensus in the data reveals that the main marine extinction happened in an incredibly tight interval of 60,000 to 100,000 years.
Okay. And during this window, global temperatures skyrocketed by 8 degrees Celsius. For our listeners using Fahrenheit, that is a spike of over 14 degrees globally.
That is a planetary fever.
A massive fever. And atmospheric carbon dioxide jumped from a relatively normal 400 parts per million to a staggering 2,500 parts per million. But wait, I have to push back on this a bit before we go further.
Sure.
How can geologists possibly know the duration of an event that happened 250 million years ago down to a 60,000-year window? I mean, rocks don't have built-in digital stopwatches.
It's a completely valid question. And for a long time, the dating of this boundary was incredibly fuzzy.
Like they just knew the rocks below a certain line had fossils and the rocks above it didn't.
Exactly. But modern geochronology has revolutionized this using something called UPEEB, or uranium-lead zircon dating. This is where the physics of crystals literally gives us that stopwatch.
How does that work? The sources mention they look specifically at 5 volcanic ash beds in a place called Meishan in South China.
Right, because those beds perfectly capture the extinction boundary in their sedimentary layers. And what they are looking for in that ash are zircon crystals.
What is so special about zircon crystals?
Well, zircon, which is zirconium silicate, is a mineral that crystallizes out of cooling magma. When the crystal lattice of a zircon forms, its internal atomic structure is perfectly sized to accept atoms of uranium as substitutes for zirconium.
Oh, okay, so it traps the uranium?
Yes, but, and this is the genius of the crystal, it completely violently rejects lead. The atomic structure just won't allow lead inside when it forms.
Wow, so at the exact moment that volcanic ash cools and the zircon crystal is born, it contains some uranium but absolutely zero lead.
Exactly.
Wait, I see where this is going. Uranium is radioactive, right? It decays over time into lead.
Precisely. Uranium-238 decays into leaded-206 with a known, incredibly steady half-life. Because we know the crystal started with zero lead, any lead we find locked inside that crystal today must be the radiogenic product of that original uranium decaying.
That is incredible. So by measuring the exact ratio of uranium to lead with mass spectrometers, geologists can calculate the age of that specific volcanic eruption.
Yes, and with an error margin of less than a fraction of a percent. By dating the ash layer right below the extinction and the ash layer right above it, they narrowed the massive die-off to that 60,000 to 100,000 year interval.
That is an astonishing piece of scientific detective work. You're using the decay of individual atoms to date the death of 81% of the oceans?
But they don't just use crystals to tell time. They also track the severity of the dying by looking at a massive, sharp global decrease in the ratio of carbon-13 to carbon-12 isotopes.
Oh, let's break down the mechanics of that isotope shift, because the sources paint such a vivid, morbid picture of what that actually means for the biosphere.
The carbon isotope excursion is really one of the most vital fingerprints of the Great Dying. Carbon comes in different stable isotopes, primarily carbon-12, which is lighter, and carbon-13, which is heavier.
Right, because 12 has one less neutron.
Exactly. Now, the enzymes that drive photosynthesis in plants and algae like rubisco have what we call a kinetic isotope effect. They're essentially lazy.
Lazy enzymes, I love that.
It takes slightly less physical energy for the enzyme to grab a lighter carbon-12 atom out of the air to make sugar than it does to grab a heavier carbon-13 atom.
So biological life naturally hoards the lighter carbon?
Yes.
Yeah.
Living things, from forests to massive plankton blooms, become highly enriched with carbon-12. The entire biosphere is basically a giant carbon-12 sponge.
So when you analyze the rock layers and suddenly see a massive, abrupt negative shift, meaning a huge spike in the amount of lighter carbon-12 flooding the environment relative to carbon-13,
It tells you something catastrophic just occurred.
it means a colossal reservoir of organic matter either died and rapidly decayed, or ancient buried life, like coal and hydrocarbons, was massively burned, just vomiting all that hoarded carbon-12 back into the atmosphere and oceans at once.
The rocks are literally recording the chemical exhalation of mass death. That negative shift is the planet suffocating on its own decomposed biomass.
And that brings up this incredibly vivid, highly debated concept from the paleontology data called the fungal spike. Because if all the forests are dying and rotting at the exact same time, something has to eat all that dead wood, right?
Right. And that is the premise behind the fungal spike theory. In the immediate aftermath of the boundary layer, researchers found a massive global proliferation of microscopic spores belonging to an organism named Reduviaspernites.
Or a Duviasprin.
Yeah, the initial and very dramatic hypothesis was that there was a brief period where fungi basically inherited the Earth.
Which is such a wild mental image.
Imagine a world where the vast, globe-spanning gymnosperm forests has suddenly died. The ground is covered in endless millions of tons of dead, rotting timber and the corpses of billions of animals.
And the fungi, which decompose dead organic matter, suddenly have an infinite food supply and zero competition. So they explode in population, creating a planetary-scale compost heap.
A completely silent, rotting world dominated by giant fungal blooms. It is a grim, almost alien landscape.
But this theory isn't universally accepted in the sources, is it? There's a lot of debate around what those spores actually were.
The debate is fierce. Critics point out that while the spike is prominent, it isn't perfectly synchronous worldwide. Furthermore, isotopic and morphological analysis led some scientists to argue that Reduviaspernites wasn't a fungus at all,
What are them?
a type of fossilized green algae.
Oh. Well, if it's algae, that changes the entire picture of the landscape.
It drastically changes the interpretation. If those spores are algal, it doesn't represent a fungal feast on dead matter. Instead, it represents the complete collapse of the terrestrial river systems.
Wait, how does algae equal river collapse?
Without deep-rooted plants to hold the riverbanks together, the meandering rivers would have broken their banks. The continents would have transformed into a landscape dominated by vast, shallow, stagnant, sun-baked puddles and lakes.
And the algae just bloomed in these stagnant waters fed by the nutrients of the dying soil.
Exactly. Now, recently, some newer chemical evidence, specifically looking at the breakdown products of these spores, has swung the pendulum somewhat back toward the fungal origin. They found fungal-specific biomarkers.
But whether it was a rotting world of fungi or a stagnant world of algal slime, it paints a picture of total ecological failure.
Absolute failure.
Let's contextualize that failure. 60,000 to 100,000 years for this main pulse to occur. Now, 60,000 years sounds like a very long time to us. Civilization, as we know it, is only about 10,000 years old.
Right.
But geologically, 60,000 years is a rounding error. It's the blink of an eye. Was this just one localized, really bad day-like an eruption that triggered a slow cascade? Or was it 60,000 continuous years of the environment actively trying to kill everything?
It is absolutely the latter. This wasn't a singular punch that the planet just took a long time to recover from. It was a sustained, relentless degradation of the environment.
The Earth's life support systems, the carbon cycle, the ocean's chemical balance, the atmosphere, were pushed entirely beyond their buffering capacities, their tipping points.
And they stayed pushed for tens of thousands of years. The pressure never let up.
Okay, so we know when the Earth's life support systems failed, and we know it was a sustained failure. But what was the engine driving this continuous horror? To find the prime suspect, we have to look at modern-day Russia.
Yes. The scientific consensus points overwhelmingly to the monumental flood basalt eruptions that created the Siberian traps.
We really need to fundamentally redefine the word eruption for our listeners here. Because when people hear volcano, they picture Mount St. Helens blowing its top, or Vesuvius burying Pompeii, a cone-shaped mountain exploding.
The Siberian traps were not that. This was a flood basalt event. This was the Earth's crust splitting open and lava just continuously bleeding out.
And the scale. The sources state the lava eventually covered an area of over 2 million square kilometers. That is a contiguous ocean of molten rock roughly the size of the entire country of Saudi Arabia.
Or Western Europe. The volume of material extruded is almost beyond human comprehension. It was enough lava to bury the entire contiguous United States under a layer of rock over 1,000 feet deep.
That is terrifying.
And this volcanism injected approximately 3,900 to 12,000 gigatons of carbon directly into the ocean atmosphere system.
But the true catastrophic twist of the Siberian traps isn't just the sheer volume of magma, right? It is where that magma was traveling and what it was interacting with before it ever reached the surface.
Exactly. Much of this magma didn't erupt out into the open air immediately. Instead, it intruded underground. It forced its way horizontally through the rock layers of the Earth's crust, creating these massive, sprawling subterranean formations known as sills.
And the crust in Siberia wasn't just inert, empty rock. What exactly was this magma violently intruding into?
The Siberian lithosphere was essentially a massive, ancient storage facility for volatile chemicals and fossil fuels. The magma intruded into massive ancient limestones and salt beds, as well as immense coal-bearing rocks from the Carboniferous and Permian
So
periods.
you have magma, which is thousands of degrees hot, injecting directly into vast underground seams of coal.
Yes, the Siberian traps weren't just a volcano. They were a planetary-scale, uncontrolled combustion engine running without a filter.
They were literally igniting and baking ancient underground coal beds. The data shows this roasting process released 3 trillion tons of carbon alongside unfathomable amounts of toxic fly ash and vaporized mercury.
And we know this for a fact because geologists found what they call paired corine-mercury spikes in the global rock record from this exact time.
What is a corn mercury spike? That sounds like a smoking gun.
It is the ultimate smoking gun. Corinine is a highly complex polycyclic aromatic hydrocarbon. It doesn't just form naturally in standard biological processes. It forms specifically when fossil fuels like coal are burned at extremely high temperatures.
So when you find corn alongside massive spikes in mercury, which is also concentrated in coal deposits layered globally right at the extinction boundary,
It proves beyond a shadow of a doubt that immense quantities of coal were being catastrophically incinerated. The underground magma acted as an oven, baking the volatiles out of the coal and rock, and venting them directly into the atmosphere.
let's put ourselves on the ground in the Permian to visualize this. You have fissures in the earth, hundreds of miles long, bubbling with lakes of lava the size of small countries.
Yep.
You have massive, dark, choking clouds of toxic coal ash billowing up, blotting out the sun and the rain. The data indicates that the eruptions emitted around 18 teratons of hydrochloric acid.
So when that mixes with atmospheric moisture, you get highly concentrated acid rain. It was literally raining acid, stripping the leaves off the few remaining trees and fundamentally altering the pH of the terrestrial soils.
But this brings up a massive contradiction that I think, a lot of people will be confused by. Normally, when we talk about volcanoes erupting, they release massive amounts of sulfur dioxide and ash that block out the sun and cause severe global cooling. Like when Mount Pinatubo erupted in 1991, the global average temperature measurably dropped for a couple of years. So why did the Siberian traps lead to 500,000 years of extreme boiling global warming?
You're hitting on the crucial dynamic of short-term cooling versus long-term warming. It's a physiological whiplash for the planet. The initial volcanic outbursts did exactly what you describe. They released monumental volumes of sulfur-rich volatiles into the upper atmosphere.
Which created global acid aerosols and dust clouds that physically reflected solar radiation back into space.
Exactly. This resulted in brief, incredibly bitter global freezes. We actually see evidence of this in glaciostatic sea level falls.
Meaning water was rapidly freezing into ice caps, physically drawing down the ocean levels. So life was initially hit by sudden freezing winters.
Yes. But here's the fatal difference between sulfur and carbon. Sulfur aerosols are heavy and they react with water. They wash out of the atmosphere relatively quickly via precipitation, usually within a few years or, at most, a few decades.
So the sulfur literally rained out.
Right. But the carbon dioxide and the methane? Those are stable greenhouse gases. They stay in the atmosphere for thousands, if not tens of thousands of years.
And because so much of the Siberian magma was intruding underground as those sills we discussed, rather than just erupting as fresh lava on the surface, there was a fatal lack of a specific geological mechanism: silicate weathering.
Exactly.
Break down silicate weathering for us. How does that normally save us?
In a normal volcanic cycle, volcanoes erupt basaltic rock onto the surface. Rainwater, which is slightly acidic from atmospheric CO2, falls on this fresh rock and chemically reacts with the silicate minerals.
Okay, so the rain interacts with the new rock.
Yes, and this chemical reaction physically pulls carbon out of the air, turns it into bicarbonate, and washes it into the ocean where it becomes limestone. It's the Earth's natural thermostat, drawing down CO2 and cooling the planet.
But in the Permian, the CO2 is coming from underground coal fires, and there wasn't enough fresh surface rock to absorb it, so the thermostat was just broken.
Completely broken. Once the sulfur aerosols washed out and the brief freezes ended, the astronomical levels of carbon dioxide and methane were left behind. They just locked the solar heat in.
The global average surface temperature eventually shot up to an estimated 35 degrees Celsius. To put that in perspective, that is an average global temperature of 95 degrees Fahrenheit.
An average.
An average of 95 degrees, meaning the equator was basically a boiling, sterile dead zone. That is a fever the planet simply could not sweat out.
Right.
So the air is now a toxic, superheated, acid-laced fog loaded with unbelievable amounts of CO2. But the atmosphere can only hold so much. Where does the vast majority of the Earth's carbon dioxide eventually go?
It gets absorbed straight into the ocean.
Which brings us to the marine nightmare.
The oceans are the great sink for atmospheric gases. But when the oceans absorb massive, rapid influxes of carbon dioxide, two primary catastrophic physiological processes occur: hypercapnia and severe ocean acidification.
Let's tackle hypercapnia first because that sounds like a medical condition.
It is a medical condition. Hypercapnia is essentially carbon dioxide poisoning within the tissues of a living organism.
So as the oceans became saturated with CO2, that gas diffuses directly across the gills of marine animals and into their bloodstreams.
Right. And when CO2 builds up in the blood, it drops the blood's pH, causing internal acidosis. That denatures proteins and triggers something called the Bohr effect, where the oxygen affinity of the animal's hemoglobin drastically drops.
In simple terms, even if there is oxygen in the water, the animal's blood can no longer bind to it. The animal essentially suffocates from the inside out while fully submerged.
It's just a horrifying way to die.
And then you couple that internal poisoning with the external destruction of ocean acidification. The data shows the pH of the ocean dropped by up to 0.7 units.
Now, zero point 0.7 units might not sound like a huge deal if you're just looking at a number on a page, but the pH scale is logarithmic, like the Richter scale for earthquakes.
So a drop of 0.7 is a massive, violent shift toward high acidity.
It changes the fundamental chemistry of the seawater. When CO2 mixes with water, it forms carbonic acid. This acid actively consumes carbonate ions in the water.
And carbonate ions are the exact biological building blocks that marine organisms like corals, brachiopods, and bivalves use to build their calcium carbonate shells and skeletons.
Exactly. When the ocean becomes too acidic, the carbonate compensation depth shifts. The water literally becomes corrosive to life. The organisms can no longer calcify their shells.
And worse, the shells they already have begin to actively dissolve into the surrounding water. The ocean was literally melting the armor off its inhabitants.
And as if hypercapnia and dissolving shells weren't enough, this leads to the terrifying sequence described in the paleontological data as ocean anoxia. The ocean suffocates.
Let's walk through the mechanics of this step by step because it's a perfect example of a cascading environmental failure. Step 1. The atmosphere is superheated by the greenhouse gases, so the surface of the oceans warms up drastically.
Correct. And this is a simple rule of physical chemistry. Warm water holds significantly less dissolved gas, including oxygen, than cold water.
Like a warm bottle of carbonated soda left in the sun, it goes flat much faster because the gases physically escape warm liquids.
Right.
Step 2. The extreme global heat causes massive coastal evaporation, creating ultra-warm, extremely salty, dense waters that sink and spread slowly across the ocean floor.
Yes. And because these dense bottom waters are incredibly warm, they are already severely depleted in oxygen from the start. This creates massive oceanic stratification.
Meaning the ocean stops mixing. Normally, ocean currents act like a giant conveyor belt, mixing the oxygen-rich cold water from the poles down to the depths.
But with the poles superheated, that conveyor belt grinds to a halt. The deep ocean becomes a stagnant, suffocating trap.
Step 3. The Siberian traps are essentially dumping millions of tons of volcanic ash across the globe, which fertilizes the oceans with massive influxes of iron, phosphorus, and other nutrients.
Which, ironically, sounds beneficial for life initially. And it is, for a very specific type of life. This massive nutrient influx triggers colossal, continent-sized microbial and algal blooms at the surface of the ocean.
The surface waters become choked with microscopic life. But then, step 4, those massive short-lived blooms inevitably die. They sink down into that stratified, warming, unmoving ocean.
And as they decompose, the billions of bacteria breaking down those microscopic corpses undergo respiration, sucking out whatever microscopic amounts of oxygen were left in the water column.
It's the ultimate biological tax. The decomposition process consumes everything.
You are left with a global anoxic ocean, a sea entirely without oxygen. The higher marine life, the fish, the complex invertebrates, die off entirely.
But the horror of the Permian Ocean doesn't stop with a lack of oxygen, because once the oxygen is completely gone, it opens the door for a different, ancient, much more sinister kind of life to take over.
I'm talking about sulfate-reducing bacteria.
This is where the story turns into a gothic horror novel. What do sulfate-reducing bacteria do?
These bacteria evolved very early in Earth's history, and they thrive exclusively in strictly anoxic, oxygen-free environments. Instead of using oxygen to breathe, They use sulfate.
And as a byproduct of this anaerobic respiration, they excrete massive amounts of hydrogen sulfide.
Yes.
Hydrogen sulfide, the gas that smells like rotting eggs. And it is highly toxic to almost all complex life. It blocks cellular respiration the exact same way cyanide does.
It does. The proliferation of these bacteria turns the oceans euxenic.
Mm.
Euxenia is the condition of being both entirely devoid of oxygen and choked with toxic hydrogen sulfide.
The deep oceans became a massive churning vat of poison.
And the data points out that we don't just have to guess this happened. Scientists found definitive chemical biomarkers, specifically a molecule called isoreninaretane in the sedimentary rocks from this period.
Isorenibutane, what is that?
It is a fossilized pigment produced almost exclusively by green sulfur bacteria.
Why is the presence of green sulfur bacteria the absolute nail in the coffin for this theory?
Because green sulfur bacteria have highly specific, rigid requirements for survival. They're photosynthetic, meaning they absolutely require sunlight to live.
Okay.
But they also require high levels of hydrogen sulfide to perform their specific type of photosynthesis. They cannot survive without both.
Oh, wow. So if we are finding their chemical remains buried in the rock records of shallow, sunlit portions of the ocean.
It means the toxic, sulfitic, euxenic waters from the deep ocean hadn't just stayed at the bottom. The rot had bubbled all the way up to the surface.
The oceans were literally putrefying. Because of these bacteria, the waters were likely a murky, toxic, deep purple and green color, constantly off-gassing the smell of rotten eggs into the atmosphere. The entire ocean was a toxic swamp.
It really was.
And this cascade of horrors perfectly explains the selectivity of the victims we talked about earlier. If you were a marine organism with a heavy calcium carbonate shell and a lazy, passive respiratory system, like a rugose coral or a calcareous sponge that just sits there waiting for water to wash over it,
You were an absolute goner.
the acidic water dissolved your heavy shell, you were physiologically poisoned from the inside out by the CO2, and even if you survived that, there was literally zero oxygen left in the water to breathe.
But if you were a highly mobile organism with active gills to continuously pump whatever water you could find over your respiratory surfaces, and you had a light shell or no shell at all to weigh you down or dissolve.
You had a fighting chance at surviving in a few isolated, shallow refuges.
Precisely. The heavy, highly calcified sessile organisms with simple breathing apparatuses suffered total ecological collapse. The organisms with advanced circulation, high mobility, and non-calcareous bodies fared much better, though better is a relative term.
Right. It was an absolute gauntlet of overlapping environmental stressors. And while the oceans were turning into this toxic, acidic, noxic soup of purple bacteria, the land was undergoing its own unique flavor of hell.
Let's shift our focus to the terrestrial collapse. The data points heavily toward extreme aridification, a severe continent-spanning drying out of the land masses.
The geography of the Earth at this time really set the stage for this, didn't it? The continents were smashed together into the single supercontinent of Pangaea.
Yes. Because it was one massive contiguous landmass, the interior was already incredibly far from the moisture of the oceans, making it naturally dry.
But the terminal Permian global warming exacerbated this baseline dryness drastically.
We actually see a distinct, fascinating physical shift in the geological fossil record, from meandering rivers to braided river patterns.
Meandering rivers are deep, winding rivers held in place by strong, muddy, root-filled banks, right?
Exactly. And braided rivers are shallow, erratic, constantly shifting channels of gravel and sand.
What does that shift from meandering to braided rivers tell a geologist about the living world?
It indicates an abrupt, severe drying of the global climate, and most importantly, a massive die-off of the deep-rooted terrestrial plants.
Because without the extensive root systems of massive trees to bind the soil and hold the riverbanks together,
The sediment just washed away. The rivers lost their structure, fanning out into shallow braids, and the landscape was stripped of its topsoil.
the collapse of the flora was absolute. The data explicitly mentions the destruction of very specific, massive ecosystems, the dense, tropical, gigantopterous rainforests of South China entirely gone.
And the vast temperate glossopterous seed fern forests of Gondwana in the southern hemisphere completely wiped from the face of the earth.
The coal swamps burned. And a massive, perhaps surprising driver of this terrestrial collapse, aside from the 95-degree heat, the acid rain, and the global wildfires, was the total failure of the Earth's ozone shield.
The destruction of the ozone layer is one of the most insidious, invisible parts of this extinction mechanism. The Siberian traps didn't just release CO2 and sulfur.
Right, as we discussed, the magma intruded into massive underground salt and evaporate
And
deposits.
these rocks are incredibly rich in halogens, elements like chlorine, bromine, and iodine. The subterranean baking of these halogens created colossal volumes of organohalogen gases, specifically methyl chloride and methyl bromide.
So when these incredibly volatile gases were vented into the atmosphere and reached the stratosphere, they interacted with the ultraviolet light.
The chlorine and bromine atoms were sheared off, and they began to catalytically rip apart ozone molecules.
Combine that with the massive amounts of hydrogen sulfide bubbling up from the rotting oceans, which also attacks ozone, and you have a chemical wrecking ball destroying the stratosphere.
That's catastrophic.
It's like taking the protective glass roof off a greenhouse in the middle of a massive solar storm. The terrestrial plants are already dying of superheated temperatures, lack of water, and having their leaves burned off by sulfuric acid rain.
And now, on top of all that, they are getting their DNA physically scrambled by unshielded cosmic radiation.
And we don't just suspect this. The sources say we have direct microscopic evidence for this radiation bombardment, don't we?
The evidence for this is incredibly elegant. Paleontologists examining the paleontological record, the fossilized pollen and spores from the end Permian, found that right at the extinction boundary, the plant spores are overwhelmingly covered in morphological mutations and severe deformities.
Spores normally form in neat, symmetrical tetrads, right?
Exactly. But at the boundary layer, they are malformed, fused, and asymmetrical. And the real smoking gun came from chemical analysis of these deformed spores.
What did they find?
They show massively increased concentrations of specific UVB-absorbing compounds. The plants were under such intense radiation stress that they were desperately altering their biochemistry to produce their own internal sunscreen.
Wow, they were getting planetary-scale sunburns.
The ultraviolet B radiation was so intense it shattered their DNA, causing widespread plant sterility and the total collapse of the primary producers in the terrestrial food web.
So the Siberian traps are undeniably the main culprit holding the smoking gun. They drove the warming, the acid, the anoxia, and the ozone collapse.
But whenever you have a crime this massive, scientists always look for accomplices.
Right. The data notes that researchers have investigated a few other mechanisms that might have piled on and made things even worse. Let's look at those. What else might have been happening?
Science naturally resists single-cause explanation for something as complex as a mass extinction. One major accomplice hypothesis involves the destabilization of methane clathrates.
Methane clathrates, or methane hydrates, are essentially highly compressed molecules of methane gas trapped inside a crystal lattice of water ice, correct?
Yes. These form under very specific conditions of high pressure and low temperature, typically buried in the sediments on the deep ocean floor or locked in permafrost.
So it's frozen methane sitting at the bottom of the sea.
And it is incredibly unstable. The theory posits that as the oceans warmed up rapidly due to the initial volcanic CO2 greenhouse effect, the warming waters eventually reached the deep ocean floor,
Which melted the ice lattices of the clathrates, releasing vast, unimaginable quantities of trapped methane gas into the water column, which then bubbled up into the atmosphere.
Exactly. And methane is a greenhouse gas that is dozens of times more potent than carbon dioxide over a short time frame. This sudden release would have triggered a catastrophic runaway feedback loop of extreme warming.
But the data seems to suggest this theory is losing ground. Why is that?
It comes down to isotopes again. The sudden massive drop in the carbon-13 isotope ratio we discussed earlier could theoretically be explained by methane clathrates, because biogenic methane produced by life, is extremely depleted in carbon-13. It's very light.
Okay, so the signature matches.
It did, initially. However, more recent and precise isotopic analysis of the rock record suggests that thermogenic methane, which is the methane produced directly by the Siberian magma baking the ancient underground coal seams, matches the global isotopic signature much better.
So the clathrates may have played a minor localized role, but the primary engine of the methane release seems to have been the subterranean volcanic oven.
Right. The volcano was the main driver.
What about biological accomplices? I read a really fascinating theory in the data about a microbe called Methanosarcina.
Oh, that is one of the most cutting-edge hypotheses regarding the carbon cycle disruption. Methanosarcina is a genus of single-celled organisms called archaea, and they are prolific methane producers.
So how do they fit into the extinction timeline?
Well, genomic analysis tracking the evolutionary history of these microbes suggests an incredible coincidence. Right around the time of the end Permian extinction, Methanosarcina appears to have experienced a horizontal gene transfer.
They basically acquired a new piece of genetic code from another unrelated microbe.
Yes, this new gene allowed them to process acetate, essentially give them the ability to rapidly and efficiently consume vast amounts of organic carbon and excrete methane as waste.
So they suddenly get this biological superpower to eat dead organic matter and pump out greenhouse gases. But they needed fuel to do this on a planetary scale, right?
Exactly. And what fueled this explosive microbial bloom? Massive amounts of nickel.
Nickel. Where did that come from?
Nickel is a crucial limiting trace nutrient for the enzymes that Methanosarcina uses to produce methane. And the global influx of nickel came directly from the Siberian traps. The volcanic eruption spewed massive quantities of nickel aerosol across the globe, fertilizing the oceans.
Wow, so the volcano provided the essential nutrient fertilizer, the dead biosphere provided the endless carbon food source, and the genetically upgraded microbes produced a planetary belch of methane that accelerated the extreme greenhouse warming.
It's a perfect, deadly biological synergy.
And, of course, whenever the topic of a mass extinction is brought up, the public imagination immediately jumps to rocks falling from space. Did an asteroid hit the Earth and cause this?
There is an impact crater that dates to roughly this geological time frame. It's the Araguaia crater in modern-day Brazil. It's a verified impact structure.
And the sources note the impact occurred in an area that was rich in oil shale. The immense seismic and thermal shock of the impact would have vaporized that shale, potentially releasing a significant localized pulse of methane and carbon dioxide.
Yes, that would have happened.
But the consensus in the data seems pretty dismissive of this being the primary trigger. I mean, the Araguaia crater is only about 40 kilometers wide. To put that in perspective, the Chicxulub crater that wiped out the dinosaurs is roughly 180 kilometers wide.
And that was a direct hit. A 40-kilometer crater is a bad day for the local continent, but it doesn't sterilize the globe.
Do we really need an asteroid when the Earth's geology was already doing such a phenomenally thorough job of destroying the biosphere from the inside out?
That is precisely the consensus view of modern paleontology. The kinetic energy released by the Araguaia impact was simply orders of magnitude too low to be the primary driver of a global, multi-pulsed mass extinction that lasted for tens of thousands of years.
It may have added a brief spike of greenhouse gases, but the Earth was already deep in the throes of a prolonged volcanic apocalypse. The asteroid was just a footnote to the Siberian traps.
Exactly, just a footnote.
Okay, so the timeline moves forward. The hundreds of thousands of years pass. The subterranean fires of Siberia eventually cool and quiet. The volcanic venting slows. The acid rains finally taper off. The air slowly, painstakingly begins to clear.
But the Earth that emerges from this crucible is completely unrecognizable.
It is a barren, scorched, silent wasteland. The oceans are depleted, acidic, and anoxic. The vast forests of the Permian are completely gone, replaced by baked mud. Who exactly inherited this post-apocalyptic world?
I think we should spend some time exploring the bizarre, almost alien recovery world, starting with the marine ecosystems.
Yeah, let's do that, because the word recovery almost feels entirely too generous to describe the early Triassic period.
It was an agonizingly slow, stunted crawl back to biological complexity in a few very specific, highly isolated areas like the Paris biota found in modern-day Idaho localized pockets of life managed to rebound and show some diversity after about 1.3 million years.
But those were extreme exceptions, right?
Absolutely. When you look at the global data, the overall marine biodiversity did not fully recover to pre-extinction levels of complexity until the Middle Jurassic.
The Middle Jurassic. That is roughly 75 million years later. The Earth's oceans were basically in a depressed, devastated state for 75 million years.
It's a staggering time frame. For millions of years immediately following the boundary, the oceans were completely dominated by a specific ecological category of organisms that paleontologists affectionately refer to as disaster taxa.
Disaster taxa. I absolutely love that term. It sounds like the name of a punk rock band. What exactly makes an animal a disaster taxon?
Disaster taxa are highly adaptable, ultra-opportunistic species that are essentially ecological generalists. They aren't the best at any one specific thing, but they can survive almost anywhere.
So when a mass extinction wipes out all the specialized, highly adapted organisms, these disaster taxa absolutely explode in population.
Right, because there is literally zero competition left. In the early Triassic oceans, we see a massive global shift. Before the extinction, brachiopods, which are these shelled, stalked, filter-feeding animals, dominated the seafloor.
But after the extinction, bivalves, specifically clams, and notably the genus Claria, suddenly replaced them as the dominant shelled animals everywhere.
Yes.
Why did the humble clam survive and conquer when the brachiopod died out? What was their evolutionary advantage in a ruined world?
Bivalves turned out to possess a much greater physiological resilience to the specific environmental stresses of the Great Dying. Their respiratory and circulatory systems were slightly better equipped to handle the low oxygen and high acidity.
Okay, so they could breathe better.
And more importantly, they occupied a broader ecological niche. While most brachiopods just sat rigidly attached to the surface of the seafloor, many bivalves were highly mobile and were excellent burrowers.
Oh, that makes sense. In an ocean where the surface water is toxic, acidic, and prone to violent temperature swings, the ability to rapidly dig down into the sediment and hide became an absolutely crucial survival trait.
The data also details a fascinating, almost comical biological response called the Lilliput effect.
Like the island of tiny people from Jonathan Swift's Gulliver's Travels, what is the physical mechanism behind the Lilliput effect?
It is a well-documented evolutionary phenomenon where the surviving lineages of species drastically, uniformly shrink in physical body size during and immediately following a severe mass extinction.
We see this occurring vividly across the Permian-Triassic boundary, right?
Yes, entire lineages of gastropods, snails, brachiopods, and microscopic foraminifera suddenly become miniaturized versions of their Permian ancestors in the fossil record.
Why do they shrink? Is it just a sheer lack of available food to grow large?
Lack of nutrition plays a role, sure, but the primary driver is actually an evolutionary physiological response to severe environmental stress, specifically the combination of extreme high heat and chronic low oxygen.
It comes down to surface area to volume ratios. A smaller physical body size requires significantly less absolute oxygen to maintain its basal metabolism.
Furthermore, a smaller body is far more efficient at dissipating internal body heat into the surrounding water. In an ocean that is essentially a hot, suffocating bath, being large is a death sentence.
Being tiny is the only way to balance your internal thermodynamics and respiration. So the oceans were literally filled with billions of tiny, stunted survivors.
Though to be fair, the data does mention a very funny, exceedingly rare counterexample called the Brobdingnag effect.
Named after the land of giants in the same book.
Right, where a tiny handful of species actually ballooned in size, likely because their specific predators were wiped out. But generally speaking, across the board, everything in the ocean got incredibly small and incredibly simple.
But this profound clearing of the evolutionary board, the wiping out of the old guard, inadvertently set the stage for one of the most important permanent shifts in marine history. It paved the way for what is known as the Mesozoic marine revolution.
Yes, let's explore the mechanics of that revolution, because before the extinction, during the Permian, the ocean was relatively static.
The data notes that 67% of marine animals were sessile, meaning they were attached, glued to the seafloor. Things like massive fields of sea lilies, crinoids, and brachiopods. They just sat there, passively filtering water, living a very stationary, quiet life.
They were the dominant architecture of the Paleozoic seas. But after the extinction, as the long, slow recovery finally took hold over millions of years, the fundamental dynamics of the ocean changed, and they changed permanently.
Complex, highly mobile communities began to vastly outnumber the simple, stationary ones. The ocean transitioned into a modern ecosystem dominated by free-moving, active predators and mobile prey.
Snails that could bore into shells, crabs with crushing claws, highly mobile modern fish, and eventually massive marine reptiles like ichthyosaurs and plesiosaurs.
Because the old, stationary suspension feeders had been wiped out, the vacant space was filled by organisms that moved.
And once organisms start moving and hunting each other, it triggers an evolutionary arms race of predation, speed, and armor defense that escalated rapidly and continues to define our oceans today.
So if the Triassic oceans were initially ruled by tiny, stunted clams and snails for millions of years before the fish and reptiles finally took over, what was wandering around on the starred, scorched continents?
On land, the reality of the recovery was equally grim and perhaps even more visibly stark. It took roughly 30 million years for terrestrial vertebrate fauna to fully recover their numerical populations and ecological complexity.
And the sheer heat of the immediate post-extinction world was so intense that it created a massive geographical dead zone known as the equatorial tetrapod gap.
Yes.
Breaking that down, tetrapod means any four-legged vertebrate animal, meaning there was a massive band across the Earth where literally nothing with four legs could survive. It was just an empty, roasting desert.
From about 30 degrees north latitude to 40 degrees south latitude, spanning the vast equator of Pangaea, the sustained extreme heat made the land entirely uninhabitable for large vertebrates.
The fossil record in these regions from this time is utterly devoid of tetrapod bones, and the landscape they were avoiding was completely transformed from the lush Permian. We see this evidenced in what geologists term the coal gap.
This is a fascinating detail.
It is staggering. The data reveals that there are absolutely zero coal deposits found anywhere globally from the early Triassic period. None. And it took a full 10 million years for coal-forming peat bogs to even begin to return to the Earth. Why did coal just stop forming?
Because the biological machinery required to make coal had been incinerated. To create massive coal deposits, you need massive woody plants, the great gymnosperm and seed fern forests.
Right. When these massive trees die and fall into anoxic swamps, their woody lignin doesn't rot completely. It compresses over millions of years into peat and eventually coal.
But those woody forests were completely dead. The deep-rooted trees were gone. Instead, the empty earth was rapidly overtaken by fast-growing, highly opportunistic coastal herbaceous plants.
Specifically things like lycophytes and the coolwort Pleuramia. These were the disaster taxa of the botanical world.
They grew fast, spread spores rapidly in the shallow, pitted river systems, and lacked the massive woody structure to ever become coal.
Okay, so the Earth is a hot, dry wasteland covered in these scrubby, fast-growing lycophyte weeds. But what was eating the weeds? We have to introduce the absolute poster child of the terrestrial recovery. This is, without a doubt, my absolute favorite part of this entire deep dive.
Ah, the Lystrosaurus.
Lystrosaurus. It is a phenomenally fascinating creature. It belonged to a group called the Dicynodonts, which are a type of therapsid.
And therapsids are often colloquially referred to as proto-mammals or mammal-like reptiles. They're on the evolutionary branch that eventually leads to us.
To picture Lystrosaurus, I want you to imagine a creature roughly the size and shape of a heavily built pig. It has a squat, barrel-shaped chest, short, incredibly powerful front legs perfectly designed for digging, and a bizarre, blunt face featuring a horny, turtle-like beak and two downward-pointing tusks.
And this weird, ugly, squat little guy absolutely conquered the post-apocalyptic Earth.
The data shows that Lystrosaurus was so successful that it made up as much as 90% of all land vertebrates in some of the earliest Triassic fossil beds.
Their sheer numerical dominance in the aftermath is staggering. It's almost entirely unique in the history of vertebrate paleontology. To have a single genus constitute up to 95% of the terrestrial biomass in some regions is unheard of.
And their success was entirely due to their specific physiological adaptations to a ruined world. They survived the worst of the extinction in the extreme surface heat of the Triassic because they were highly efficient burrowers.
Their powerful forelimbs allow them to dig deep underground tunnels, escaping the 95-degree surface heat, the harsh UV radiation, and the poor air quality.
Their barrel chests housed massive lungs, an adaptation that allowed them to extract what little oxygen was available in their subterranean burrows, which would have been highly hypercapnic filled with CO2.
Furthermore, they had that specialized beak. They didn't need lush, nutritious leaves. That beak could shear off the tough, fibrous, nutrient-poor disaster taxa plants like Pleuramia that covered the surface.
They also exhibited strong grouping behavior, living in massive huddled herds, and they clearly bred incredibly fast. I just marvel at the resilience of Lystrosaurus. It's like a post-apocalyptic rat or a cockroach that suddenly finds itself the dominant, largest animal on planet Earth simply by virtue of outlasting everything else.
Exactly.
Imagine for a second walking across the massive supercontinent of Pangaea. You walk from what is now Antarctica all the way up through Africa to modern-day Russia. And 9 out of every 10 animals you see on this months-long journey is this exact same weird, tusked, burrowing pig reptile. It's a completely wild, almost surreal image of Earth.
It is a profound testament to the reality of natural selection. Evolution does not always favor the biggest, the fastest, or the strongest. In times of crisis, it ruthlessly favors the adaptable.
Lystrosaurus could survive on meager vegetation, dig a deep hole to hide from the sun, and multiply rapidly. In a ruined world, those were the traits of a king.
But the reign of the pig lizard didn't last forever. As the Earth slowly healed, new players entered the game. Which brings us to the profound evolutionary shift known as the Triassic takeover.
And how this exact sequence of events directly forged our own mammalian ancestry.
This is where the deep history of the rocks connects directly, intimately to human biology. Before the Great Dying, during the Permian, our distant ancestors, The synapsids, specifically the advanced therapsids, were the undisputed dominant rulers of the land.
They occupied all the apex predator and mega herbivore niches, animals like the sail-backed dimetrodon or the massive saber-toothed gorgonopsins.
But the Permian extinction utterly devastated them. The massive apex predators starved or roasted. And while the humble ichthyosaurs had a remarkably good run in the immediate empty aftermath, a new, highly competitive group eventually rose up to seize the vast, vacant ecological niches as the Triassic period marched on.
This group was the archosaurs.
Yes, the archosaurs are the evolutionary ancestors of the dinosaurs, pterosaurs, crocodilians, and eventually modern birds.
As the Triassic climate stabilized, the archosaurs rapidly diversified. They were incredibly efficient, they developed superior terrestrial locomotion, many becoming bipedal, and they became highly successful predators and herbivores.
This rapid marginalization of the older lineages is the Triassic takeover. The archosaurs relentlessly outcompeted and pushed the surviving therapsids, our direct ancestors, into the absolute furthest margins of the terrestrial ecosystem.
And here is the massive, mind-blowing aha moment of this entire deep dive. Pay attention to this mechanism. The archosaurs, the early dinosaurs, were primarily diurnal, meaning they were awake and active during the day.
They claimed the sunlight. They took over the daytime dominant predator roles, the big herbivore roles, the entire open landscape.
So our proto-mammal ancestors, if they wanted to survive, if they wanted to avoid being eaten by a fast bipedal archosaur, were forced into a very specific, highly restricted lifestyle.
They had no choice. To survive the Triassic takeover, our synapsid ancestors had to become tiny nocturnal insectivores. They had to live in the literal shadows.
Hiding in burrows during the day, coming out to hunt bugs only in the cold, dark night when the archosaurs were sluggish or asleep.
And living in the cold, dark night for tens of millions of years forced incredible, defining evolutionary changes upon our biology.
Let's trace the causality here. If you are a small animal hunting at night, the sun isn't there to warm your body. You need to generate your own heat to move fast enough to catch a bug. Boom! The evolutionary pressure forces the development of endothermy or warm-bloodedness.
Exactly. But generating internal heat is energetically expensive. You can't just let that heat bleed out into the cold night air. You need insulation. Boom, the scales change, and you develop hair, fur.
The physical adaptations compound upon each other. You are hunting in the pitch black. Your eyes are less useful. You desperately need to hear the tiny scuttling of an insect or the quiet footstep of a nocturnal predator.
Boom, evolutionary pressure drastically modifies your jaw structure. Bones that were formerly at the back of the reptilian lower jaw detach, shrink, and migrate up into the skull.
To become the inchimicus and malleus, the complex, hypersensitive mammalian middle ear bones. You sacrifice jaw strength for incredible high-frequency hearing.
You also need massive amounts of energy to maintain that warm body heat and fuel that active nocturnal lifestyle. Boom, you develop a secondary palate so you can chew and breathe at the same time, and your metabolic rate skyrockets.
It is a stunning realization. The pressures of being marginalized by the archosaurs stripped away our reptilian traits and shaped the defining characteristics of what it means to be a mammal.
We literally lost some of the color-sensitive retinal receptors in our eyes that reptiles and birds still have, simply because our ancestors were hunting in the dark for so many millions of years and didn't need to see color.
So think about the cascading domino effect of this history. If the Siberian traps had never erupted, the massive dominant synapsids might have just continued to rule the Earth uninterrupted.
The archosaurs might never have found the empty ecological space to evolve into the mighty dinosaurs.
And if the dinosaurs didn't take over the daytime, mammals might never have been forced into the night to develop fur, warm blood, and complex inner ear bones. We are quite literally the children of the great dying.
Every mammalian trait we possess, the very fact that we are warm and hairy and can hear high pitches, was forged in the crucible of this post-apocalyptic, dinosaur-dominated world.
It is a profound, humbling realization of our place in the web of deep time. But this ancient history, as fascinating as it is, isn't just a curiosity locked in the rocks. The mechanisms we've discussed today hold up a very clear, very stark mirror to our present planetary reality.
Which brings us to our final overarching theme, the echoes of the Permian in the present day.
Right. The geological and paleontological data we've been reviewing make it abundantly, repeatedly clear that geologists frequently and deliberately compare the mechanisms of the Permian-Triassic extinction to modern anthropogenic, meaning human-caused global warming.
And, to be completely objective and precise with the data, the scientific parallels are stark, and they are entirely rooted in physical chemistry. Both the Great Dying and our current climate crisis are fundamentally driven by the massive, rapid release of carbon dioxide and other greenhouse gases into the atmosphere.
And physics does not care where the carbon comes from. Whether it's an underground magma sill baking Permian coal or an internal combustion engine burning refined petroleum.
The input triggers the exact same mechanisms. Global temperature increases, severe ocean acidification as the seas absorb the CO2, and the resulting drastic drops in marine dissolved oxygen levels.
The records do note a terrifying modern distinction, though. The current rate of human greenhouse gas emissions, the sheer speed at which we're pumping CO2 into the air, is actually happening faster than the average rate of release during the Permian-Triassic event.
The Earth is gaining carbon faster now than it did when a continent was on fire.
The total volume released by Siberia was vastly larger over tens of thousands of years, but our speed of injection is unprecedented. The mechanisms, the physical chemistry of what happens to the Earth's oceans and atmosphere when you do this are chillingly identical.
To crystallize this point, let me quote directly from the text provided by geologist Lee Kump, whose research focuses heavily on these oceanic transitions. Analyzing the Permian, he states, "The Permian-Triassic mass extinction provides a stark reminder of the consequences of rapid carbon dioxide emissions. The geological record shows that once these tipping points are reached, the cascading effects on ecosystems can last for millions of years."
That concept of a cascade is exactly what I want you to take away from this. In modern public discourse, we often reduce climate change to just things getting hotter. We think of it as a localized inconvenience. Oh, the summers will be warmer, the storms might be worse, we'll need more air conditioning. But this deep dive into the Permian shows us the true, terrifying nature of the domino effect. It's a linked biochemical cascade. Carbon dioxide goes up, which mathematically forces ocean acidification,
which directly leads to the calcium carbonate shells of marine life dissolving,
which disrupts the biological pump leading to ocean stratification and anoxia,
which provides the perfect environment for toxic sulfate-reducing bacteria to bloom,
which releases hydrogen sulfide into the air, which floats up and catalytically shreds the ozone layer, which sterilizes the plants on land. It is never just one thing. It is a systemic, interconnected failure of the entire biosphere's life support mechanisms.
The Earth's environment is highly integrated. What the Great Dying teaches us, unequivocally, is that when you rapidly and violently alter the fundamental chemistry of the atmosphere and the oceans, the consequences do not stay isolated.
They ripple through every single trophic level, crossing from the deepest, darkest ocean trenches up into the highest reaches of the stratosphere.
So let's pull back and look at the enormous journey we've just taken. We started on a thriving, incredibly diverse Permian Earth, walking through forests of giant ferns, watching massive saber-toothed synapsid rulers stalk their prey.
We witnessed the onset of a volcanic apocalypse of unimaginable, continent-shattering scale. 2 million square kilometers of lava, underground coal fires burning for millennia, rain turning to hydrochloric acid, and the oceans literally rotting into toxic purple stews.
We saw the vibrant Earth reduced to a miniaturized, baked, scarred Triassic wasteland, inherited entirely by burrowing, pig-like decinodonts and tiny, desperate clams.
And finally, we traced how that empty, hostile world eventually birthed the archosaurs, driving our own terrified ancestors into the freezing night, fundamentally shaping the very physiological nature of what it means to be a mammal today.
It is the ultimate dual-sided story of absolute destruction and relentless resilience. Life ultimately endured the absolute worst the planet could throw at it, but the cost of that endurance was near total annihilation, and the physical recovery of the biosphere took tens of millions of years.
As we close out this deep exploration into the ancient past, I want to leave you with one final, deeply haunting concept drawn from the paleontology data. It is a specific technical term used by researchers, and it is called dead clade walking.
It is perhaps the most grim phrase in all of evolutionary biology. Dead clade walking refers to a species, or a whole group of species, that technically managed to survive the initial pulse of a mass extinction. They physically made it across the Permian-Triassic boundary.
But the reality is their populations were so severely genetically bottlenecked, or their required ecological networks were so fundamentally, permanently destroyed that they had no future.
They essentially staggered along for a few million years in the early Triassic, a shadow of their former selves, before quietly, inevitably going completely extinct without ever diversifying or recovering again.
The snail family Bellerophontidae is a textbook example of this. They technically survived the Great Dying, but they were dead clades walking. The clock had already run out, they just hadn't fallen over yet. So here is the thought I want you to sit with. to truly mull over as you look out at our modern, rapidly changing world today. As we observe the rapid alteration of our own planet's atmospheric chemistry with unprecedented carbon emissions, as we watch the great coral reefs bleach and dissolve, and as we measure the silent, staggering plummet of global insect populations, how many of the vulnerable species we are desperately trying to conserve and save right now are already dead clades walking?
Are we looking at viable animals, or are we simply watching the lingering ghosts of an ecosystem that, chemically and physically, no longer exists, staggering toward an inevitable, predetermined end?
Thank you for joining us on this extensive deep dive into the Permian Triassic extinction. Keep questioning the world around you, keep learning, and keep exploring the deep, ancient, terrifying history buried right beneath your feet.